What's the fastest way for us to get from one point to another? It's kind of obvious that it's a straight line, right?
It's not always like that.
Today's challenge is this. We're going to release a little ball from up there, and it has to reach the end down here. What we're going to test is which ramp makes the ball get here the fastest. And the winning ramp is the one with the Brachistochrone curve.
Brachistochrone comes from the Greek brachistos, meaning shortest, and chronos, meaning time. And this challenge has already made many people in ancient times use their brains. Now it's your turn to be tested.
Let's get to work.
A straight line and a curve. So Iber, are you still sticking with your guess?
At first glance, he'll go down the straight faster. That's what we picture, the shortest path. If he were going to be faster on the straight, we wouldn't do this since it's too obvious. So, since it's not obvious, I think it's better to test it. Here we go. Let's do it, Ree, and go.
By a long shot, Iber.
Oh my goodness.
No.
You can see that it's not that intuitive. It's not obvious, but it's going to get a lot worse because Pena made some other drawings of descents here. And if you thought that from now on, whenever there's a curve, the curve is faster. Maybe it's not exactly like that.
So let's set up the others. Here we have two ramps, but they start exactly the same. The only difference is that one goes underneath and the other goes over the top. This one is the shorter path.
Now, I'm getting smarter. I'm going to bet on the one that goes down. Yeah, that's the one that's going to go faster, right? Let's release them a little lower down because those little balls from Pena are trying to do some crazy stunts here. But it works. The logic is the same. What's up? I think I got it right this time, huh?
What's up, Bern? How is that possible? This one clearly has a longer route.
In theory, when you release the balls, they're at rest, and what gives them acceleration is that they start going down. And when things fall, they accelerate, right? So it's like when it's falling, it's as if we're stepping on a car's accelerator. So here, the acceleration is the same, but when it gets here, this one's acceleration keeps going. In other words, here the guy took his foot off the accelerator, and here it kept accelerating. Oh. In this part, the ball that's lower is much faster.
And we can see that it pulls ahead.
Here it clearly pulls ahead. At the end, there's a ramp, which is like a brake. So, but the ramp is exactly the same size as the descent. So it makes up for that drop. And it ends up reaching the end ahead because it covered a large part of the path much faster.
So if this part of the path that it travels faster is long,
It will get even further ahead.
it gets further ahead.
Now, it's the same thing that happened on the other ramp. On the straight ramp, the acceleration is constant along the way. On the curved one, it accelerates a lot at the beginning and just a little at the end.
So even though the path is longer because you're going faster and you accelerated earlier.
You get there faster. Pay if it pays off.
Calm down, Iber. There's one more.
Now he's in trouble since this W shape means he'll lose regain, then lose acceleration again. I doubt this will be the fastest.
It won't be the fastest, but it'll be quicker than this one.
I think so. I think this curve will still be faster than the straight line. So my bet is the middle one wins the race. The curve comes in second and the straight line comes in third. Let's see. 2, 3, and go. I think I lost, right? You lost. No, I got first place right, but the straight line was faster. It was faster.
So it's not always worth it. That's today's lesson.
Now, we have an interesting question here, since, depending on the way the ball goes down, if it goes down more or less, If at the end it has to go up just a little, this makes the ball go down faster or slower. What is the ideal shape for it to go the fastest of all? What is the so-called Brachistochrone?
This problem isn't easy at all. In fact, a lot of people have studied it, including someone named Galileo Galilei. Have you heard of him?
I know him, Pina. In fact, I have a rivalry with this Gallo. Once we tried to make Galileo's thermometer here on Manuel do Mundo. It's one of the most beautiful things I saw it as a physics experiment. It took us a week and everything went wrong. But anyway, for those who don't know Galileo yet, he's a very important guy in astronomy because he was one of the first people to observe celestial bodies using a telescope. So the first detailed drawings of the moon were made by him. He discovered 4 moons of Jupiter, which we call the Galilean moons. And even more important than that were his studies on motion.
Exactly. He loved to measure and see how things moved. And this has everything to do with motion. So obviously he tried to solve the Brachistochrone problem.
But did he succeed? Or was it like in that experiment of his that we tried to recreate where everything went wrong?
He said he succeeded. He said that the arc of a circle was the ideal shape.
The circumference is this right here. The difference between a circle and a circumference. That the circle would be like a whole pizza, including all the middle part. And the circumference is just the edge of the pizza. And the arc of a circle is simply a piece of that edge. So if we take this part from here to here, for example, that's an arc of the circumference. If we take half from here to there, that's also an arc of a circle. If we take just a tiny little piece, that's also an arc of a circle. Is the ideal arc of a circle for going down a big, more curved arc, or is it an arc that's almost straight?
That's the issue. You have multiple arcs between 2 points. Which one is called the Brachistochrone? And Galileo was trying to figure out which one it was, but does any of them work? Are the two equivalent?
Let's test it. Let's see. Here we have the line that was there at the beginning as well, and 2 arcs of a circle. This one is a giant circle. The middle one is a huge circle with a piece removed, and the last is a slightly smaller circle. Now, there's a question here, right? This one in front goes down. The ball even goes below the finish point. It'll have to go up just a little at the end.
However, it also accelerated more.
Accelerate more. I would bet on her.
Let's see.
Let's see. Girl, I think you won. I told you I was going to win.
That means one thing, Ibra, that the arcs aren't the same. They're not equivalent.
In the end, Galileo didn't find it then.
No, he just used a trick. But there were guys who found it. 696, Johann Bernoulli, he decided to propose this challenge to everyone. He said, no, this deserves more attention. And he himself solved it in 2 weeks.
And what's the shape?
It's not any arc of a circle. It's something called a cycloid.
It's this little blue one.
Yeah, we have a wheel spinning, and if we track any point on the edge of the wheel,
It will form this, can I call it an arc?
it's an arc, but it's not a circular arc.
Okay,
So, it's a cycloid because it's formed by something cycling.
and we put this here on the ramp.
Yeah, if we take a shape that fits exactly between the 2 points, it will theoretically be our Brachistochrone. It says Brachistochrone,
Will it?
it will.
Now, we know the name of that shape we made with the bicycle tire. In that video where I put the Arduino on the bicycle tire and we took a long exposure photo, right? It's a cycloid. What is it? 2 crazy guys kneeling on the floor with chalk in hand, a piece of a circle. They're drawing the cycloid of the Brachistochrone. Pina, I'll tell you that at first glance, it looks like an arc of a circle. If it weren't for the very end, which is just a little bit higher.
Yeah, looking at it over short distances, it really is deceiving, but it's not an arc of a circle, and that's the best part. We made a little ramp exactly.
Our cycloid. Yeah, look at that F. Now that's it. Now it's time for the battle of the century. Let's see if the cycloid is really the best.
Brachistochrone.
Brachistochrone. Brachistochrone. No, it's Tachrona. Tron from Kronos. Ha. 2, 3, and go. I think the softs themselves won, man. Ooh. It won the race by far.
There's something cool about this Brachistochrone, right? The one who discovered it was Johann Bernoulli. It took him 2 weeks, right? Okay, then he got all proud and said, who am I going to challenge? Newton. So Newton at that time was already older, already in his 50s, kind of retired. Newton.
Which curve works best? Yeah.
And then Newton received this challenge at 4 in the afternoon, and by 4 in the morning, he was done.
Newton never disappoints.
But it's not over yet. There's one last surprise. I'm going to release 3 balls from 3 different points.
All right.
Which do you think will reach the lowest point there?
Look, the lowest point is here. Not at the tip here.
That's it.
The yellow one, this one here, has less distance ahead. Did all 3 pass together, or is it just me? Releasing became harder, so we improvised a new release mechanism. I'll admit that now. It's harder to understand why all 3 reach the same point. Like, is the acceleration of the one that's farther away really that big for it to catch up here at the end?
It was a question that mathematicians Euler and Lagrange asked themselves. Is there a curve where, no matter where you start, it will always take the same time to get there? And they solved a complicated equation and found a solution. And the solution is exactly the cycloid. So it has these 2 properties. Not only is it the fastest way to reach any other point, but it takes the same amount of time from any point to the study of this curve called the Tautochrone. Tautochrone, Tautochrone. Tauto means same. Chronos, it means time.
Same time.
This is how Euler and Lagrange developed variational calculus, which is a very important foundation that we still use today in differential calculus to find functions and exotic curves like this one.
3 new words for you to add to your vocabulary today.
Brachistochrone,
Cycloid and Tautochrone. Got it.
But what really matters is that science has won again.
Yeah. Until now, we had half a Brachistochrone. Ina wanted to connect one to the other to form a complete Brachistochrone, so that when we rolled the balls from both sides at different positions, they would meet perfectly in the middle. They would hit exactly in the middle. But, when it comes to cutting it in half, there are some inaccuracies. We weren't doing everything with ultra-precise machines. So if it works out, it's because something is wrong. 2, 3, go. Ah! Ah! Ah!
My God! My thigh!
I insisted the same person released it. No, it hit dead center. Too bad we can't do slow motion, since we recorded at 24 frames per second.
And we're not going to do another one.
No, otherwise it might go wrong next time. No, let's do it like this. Was it luck or not? 2, 3, go! It's perfect, man.
Man, this works!
Let's see. Only slow motion tells the truth in this video. Actually, this is exactly the same experiment as before, just done in a different way, right?
Yeah, we set up a complete cycloid. That's right. If the time it takes from any point to the middle is the same,
it doesn't matter where we release it from.
Any 2 balls meet in the middle.
What if we overdo it? Put it at the start, and I'll add it here.
Do you think it will? It's just that friction might start to have an effect, but let's go. Let's do it.
2, 3, go. One jumped over the other. Let's try again, but no accidents this time. 2, 3, go.
You were also a little late.
Right? Yeah, mine was a little late, but it's close.
No, but it is.
Okay.
It makes the point.
Given our level of precision here, I think the point stands. Yeah. 1, 2, 3, and
1, 2. If you like this marble race, we did a really cool experiment showing the distortion of space-time using cloth and several marbles as planets. It's really cool,